of how we're going to solve. I would like to make one clarifying point. Last time as I was drawing the board over there, I put u as a function of y. U is in fact a function of x and y. Now the explanation of how that came to that point is a little complicated. Suffice it to say that in general, the profile of y, the profile of u in the boundary layer is geometrically similar as you progress through the boundary layer. So the solution can be obtained by taking, for example, a polynomial expression to try to describe the curve and then multiplying it by a function of x. I can see you're all very into this guide. But we'll leave that with that right now. But it is a function of x and y. All right, so how are we going to solve this? So what is the solution formulation? And I'm not going to, and you'll be relieved to know we're not going to go through we're not going to go through the whole simulation. It'll take another lesson and a half. First of all, you got to understand that this particular solution is complicated because all three governing equations are coupled. And that's because T appears in the momentum equation. In any case, the solution can be found by non-dimensionalizing. The first step in finding a solution is to non-dimensionalize the governing equations. And open your books now to page 587, I think, and look at equations 9 and 10. So the solution depends on non-dimensionalizing governing equations. And I'm not going to write those up here. You can look at them in the book because we're not going to use them other than to say that's how the solution starts. And out of this comes the Grashof number, which we're going to take a look at for a second. And what is the Grashof number?
Combination of Reynolds number and the
Pardon me?
combination of Reynolds number and the
Yes, it is. It is a yes. But what does it physically represent?
expansion.
It's in there. It's a ratio of the buoyancy forces to the viscous forces. Okay? So the Grashof number. And let me ask you a question. One more. What does the Reynolds number represent? Pardon me?
Viscous forces.
I can't hear you.
Isn't that the viscous forces?
And I still can't hear you, China. I'm getting deaf.
Viscous forces.
2 compared to what?
Oh, compared to the pipe.
Now, open your books to table 6.2. I mean, you're halfway there. All right, open your books to 6.2.
Should never spoke up.
What does it say? Right, the inertia to the viscous number. So the viscous forces. So what we're trying to do is we're comparing two different things: the inertial forces and the buoyancy forces. Both are being compared to the viscous forces. So the Grashof number, which given the symbol GR is equal to G, from your homework you know this, beta times TS minus T times the characteristic length cubed over nu squared. And as I've already said, it is the ratio of buoyancy to viscous forces. That leads to some interesting results. If we take a look at the Grashof number and compare it to the Reynolds number squared in one column, the dominant form of convection that based on that ratio, and the general result in terms of formulation of a correlation to predict the heat transfer coefficient, we get the following results. And we have three different cases. One, where this ratio is approximately equal to 1. And in that case, both forms of convection, free and forced, are approximately equal. And the general result will be a Nusselt number, which is a function of the Reynolds number, the Grashof number, and the Prandtl number, typically. And if in fact you have a case where the Grashof number divided by the Reynolds number squared is significantly greater than 1, then you have free convection being dominant, and you'll have a Nusselt number relationship, which is a function of the Grashof number and the Prandtl number. And if you have, conversely, this ratio being much, much less than 1, then you have forced convection being dominant, and you will see the types of empirical relationships that we've already experienced in Chapter 8, which is Nusselt number being a function of the Reynolds number and the Prandtl number, such as the Diels-Boulder and the Seidertate equations. All right. All well and good. Yes?
What does the third one in the middle say?
Free convection?
Third one, down.
Forced convection?
Forced convection, okay, thank you.
Okay. All right. So what is the solution to this? Well, the solution is, and I don't know who's given credit for this, is, there's no name associated with it, is another similarity solution. And there are two variables introduced. Once again, eta, for this case, eta is equal to y over x times the Grashof number, function of x over 4 to the 1/4, and psi, which is a function of x and y, is equal to function of eta. This should all look painfully similar to the Clausius solution, times quantity 4 nu times the Grashof number, again, function of x over 4 to the 1/40 power. And these equations are in your books. And the solution, we're not going to go through it here, but you can see the outline sketch of the solution on on pages 568 to 570 of your text. Okay? And what happens is you end up with a numerical solution to differential equations, ordinary differential equation, much like we did in the previous case. And we're going to see what that result is in a moment. There's another way to do this. It used to be in the Incompare IntuIt book, but they took it out. It's kind of interesting, and that was an integral approach, an integral solution of a polynomial. And I'm not quite sure why they took it out. Over the years, they've taken a lot of stuff out. They put some stuff into the textbook as well. But that's an interesting solution. We don't do anything like that in the course now. It was just an interesting solution. We used to take a whole lesson on that. I'm not, in retrospect, I'm not entirely sure that was the most productive use of the lesson. But anyway, we used to use a whole lesson on that. Side point. In either case, what we obtained from this solution was an expression. The result was an expression for the partial of t with respect to y evaluated at y equals 0, which also should look very similar to you, which was then substituted into the energy balance at the wall. Again, a technique which should be very familiar to you. So if we look at that energy balance at the wall, H is equal to minus k times the partial of t with respect to y, evaluated at y equals 0, over ts minus t infinity. Okay. And from the similarity solution, there was a numerical evaluation. There was a numerical evaluation of the differential equation, and you ended up with the following result. Nusselt number equal to a function of x is equal to Grashof number x over 4 to the 1/4 times g times the Prandtl number. Now, caution for a moment, everyone needs to pinch themselves if they're not fully awake. You're going to get a free convection problem on your exam. And you're not going to use this equation, but you're going to use a variant of this equation, which we're going to talk about here in a moment. One of the problems that people do is that they look at that equation and say, okay, this is easy, Grashof number, look up the Prandtl number, multiply it by 9.807. Except, this is not g, gravity, it's g, a function of the Prandtl number, which is equal to the following extraordinarily ugly thing. All right, 0.75 times the Prandtl number to the 1/2 over 0.609 plus 1.221 times the Prandtl number to the 1/2 plus 1.238 times the Prandtl number, and that whole thing to the 1/4. Okay? You can't make this stuff up. All right. This is equation 919. And don't get too attached to it because we're not going to use it very much. All right? Equation 919. But that came from the similarity solution. And this is equation 920. Also a result of that solution and a graphical analysis. All right, conditions on this. Just to remind you, include laminar flow, laminar free convection, and what type of geometry?
Vertical flat plate.
Vertical flat plate. Okay, so there is an analytical solution based on this similarity solution for that. You get a similar result in terms of the results if you go with polynomial curve fit as well and integrate. However, I may want to, let me just add one more thing. In the interest of time, I'm not going to go through the integral. It's in your textbook. But I would point out equation 921, which is the next equation in your textbook. And that is an average value. This is a localized Nusselt number, no bar. Okay? Localized Nusselt number. Look at equation 921 in the next page. If you integrate this over the length of the flat plate, you come out with the same result, except this result is multiplied by what, Brianna? Allie? 4/3. Okay? I'm not even going to take the time right now to write it. Why? Because we're not going to use this equation. Okay? All right. All righty. Let's take now a look at the empirical correlations. These are what you're going to use. So, you should have your book tabbed. And the tab for chapter 9 is the free convection correlations. Okay? Look at this right here. Open your book now, and I'm going to talk about that. Keep one finger on these as I refer to the different correlations in your book. The first thing I want you to do is I want you to take and cross out in the table for cases 1, 2, 926. I'm going to have you use 924. It is much simpler. It gives sufficient results, and that's what we're going to use. That's your expectation for them. Now, if you want to use 926, you're welcome to do so, and I will not going to count you wrong. But 924 is much easier and straightforward way to use. Okay? So cross that out and put in 924 rather than 926. So now we're going to talk about these empirical correlations. All right. Now, unlike the Blausius solution, which we do use, the reason we don't use this similarity solution is because it's relatively restrictive, okay? And we're going to be able to use the equation 924, which I'm going to talk about here in just a moment, for both laminar and turbulent cases, okay? So you can use it for both laminar and turbulent. Now, if you, let's open your books now to, keeping one finger on this, I want to show you, I want you to look at how this table 9.2 is arranged. In the leftmost column, you have the geometry which is under consideration. The first one is a vertical plate. The next one is an off vertical plate. It is a plate which is inclined at some angle. The next one is flat surfaces. And look at what this says here, because it's very careful. You got to be very careful. It can be a cold surface up, or a cold surface up, or a hot surface down. All right? Or that's for the bottom one. Or a hot surface up or a cold surface down for the one above it. Okay? And you can see there are different correlations for those different cases. We're going to look at those correlations in a moment. Turn the table over, and you have the other two geometries which we commonly use. One is the infinite cylinder. That would be your pipe, okay, running. And that's equation, that should be equation 933 instead of 934. And the sphere is equation 935. All right, over in the next column is the recommended correlations, and we just gone through those, or in some cases suggested you change them. And then restrictions are shown in the last column. Okay? So now let's take a look in your book at equation 924. That is on page 572. And this is equation 924. And that is the Nusselt number over the length of the plate is equal to C times the Rayleigh number L to the n power. It's equation 924. This can be used for either vertical flat plate or inclined flat plate. It can be used for laminar, and it can be used for turbulent flow. By the way, what is the anyone know from the reading? What is the breakdown for laminar and turbulent flow? We'll just make a note here. Okay, laminar flow laminar flow is when the Rayleigh number is less than 10 to the 9th. And turbulent flow is when the Rayleigh number evaluated at the end of the is greater than or equal to 10 to the 9th. Now, why is that important here? Let's look carefully at the text surrounding this equation. Look underneath, it should be highlighted. L is your characteristic, okay, 924 is at the bottom of the page. It contains the Rayleigh number. Jump to the top of the next page, okay? Look at what it says there. There is the Rayleigh number. It is a function of the Grashof number times the Prandtl number, okay, as we suggested it would be. Pretty easy stuff, really, when you come right down to it. And you see the G there is gravity, okay? And then come down and note underneath that N is equal to 1/4 for laminar and 1/3 for turbulent. So you have to choose the right, the right exponent there. All right? And then, this is what's a little confusing. Note that the properties are evaluated at the film temperature. Okay, that's in that same paragraph. Go down to the next one, because this is where it gets a little complicated. You would think that they would have said something about C. All right? There's nothing about C. So don't panic if you're using this equation. What are you going to do? You're going to look down at the next paragraph. Expressions of the form given by equation 9.4 have been developed for the flat plate. For laminar flow, N is equal to 1/4 and C is equal to 0.59. And for turbulent flow, C is equal to 0.1 and N is equal to 1/3. All right, I don't know how to tell you that other than you can write it somewhere if you want to. Put it in table 9.2, I don't care, but there's where those values are. Now, if you take a look at 926, the beginning and 927, you can probably gather why I said let's just use 924. Okay? They're very complicated, and we're not designing anything that's critical here, so I just want you to be able to notice that it's a free convection problem and solve it. Okay? There are more sophisticated empirical relations out here. Okay? Any questions? So what is this for? This is for vertical and inclined plates. What are we going to do for an inclined plate? JJ? What are we going to do if it's an inclined plate? What if the plate's inclined at 30 degrees?
Use equation 9.24.
Yes. What are we going to do with 9.24? Stephanie? Right. You're going to replace. Look at table 9.2. You're going to look at, you're going to take table 9.2, you're going to use the same correlation, but instead of G in the Rayleigh number, you're going to use G times the cosine of theta.
So after 60 degrees, do they consider it over?
Yeah, well, I'm not going to give you one that falls into that another region. I guess after 60 degrees, the correlation just does not perform very well. And it probably is, I don't know. I don't know whether you'd be better off using one of the horizontal plates. I don't know. As a matter of fact, unless someone has seen it in there, to the best of my knowledge, I don't believe they address that issue at all in the textbook. And I don't.
It's closer and closer to one, so I don't see like why they would push it.
Yeah, well, I'm saying that they probably, if I had to take a guess, if I was over 60 degrees, I'd probably go with a horizontal flat plate correlation. I don't know. It's kind of a little black area, undefined. Or at least as far as my knowledge of the situation is undefined. Somebody out there, I'm sure, knows exactly what it is, but I'm not that person.
Just don't build them like that.
Well, I'm not going to give you a test question on that. So, there you go. Okay? But you may get an inclined plate, and you may get a horizontal plate. But I'm not going to give you a plate at 75 degrees. Okay? So, rest easy on that. All right. Any questions on the vertical flat plate correlation? Yes, sir.
Is theta from the vertical or from the horizontal?
It is from the, that's right in here. It's from the vertical.
Okay.
Yeah. Okay? It shows it on page 577.
It literally says for the opposite surfaces, no recommendations are made, and the literature should be consulted.
Yeah, for the opposite surface, yeah.
So weird.
Yeah. This is generally recognized as the best heat transfer textbook, at least at the undergraduate level. And I got to tell you something, if you go to graduate school, hang on to your ink compared to WIT, because most of the textbooks they use at the graduate level, depending on who you get, are totally indecipherable. So, this is a good book. It's a really good book. Yeah, you can get some really strange textbooks at the graduate level, depending on who happens to be teaching the course. All right, any questions? All right, then let's move down in Table 9.2 to the next area, which are the horizontal surfaces with hot and cold surfaces, respectively, up or down. All right, what equations do they say you're going to use on those? Equations 930, 931, and 932. So please open your textbook now to page 578, and let's take a look at these equations. Nothing exciting about these equations. They're both straight. All three of them are straightforward. They are simply the Rayleigh number with a coefficient and an exponent in all three cases. Note, for the case of the upper surface of hot plate or lower surface of cold plate, you have different, between 930 and 931, you have different criteria for the use of those two equations. So evaluate your criteria and select the equation that matches the criteria. All right? There's only one equation for use for the lower surface of a hot plate or upper surface of a cold plate. And people always say, well, what if the number's close, but it's a little outside of the range? Well, you have nothing else to use. So you'd use this equation. Although, typically, what really happens is you get, how do you deal with the problem when your Rayleigh number is really, really low? Anyone wager an explanation for that?
Assume laminar flow.
No, because this is already laminar. Laminar flow is this criteria. What if your Rayleigh number is 10 to the 4th?
Assume no motion.
Assume twice fluid. That's how you would do this. And so now you'd solve it like a twice fluid problem. Okay? All right.
Do we see that on the exam?
No, I'm not going to throw you. I don't throw you oddballs on the test. I don't think I need to do that. To be honest with you, I think the stuff is hard enough without causing you to do too much. Yeah. By the way, those 3 problems on the last homework were all test problems. Now they weren't on the same test, but yeah. All right. Okay. Any questions on 930 or 931? I mean, these are pretty simple stuff. Just got to know where to use the equations. All right, so let's go back to table 9.2 again. And now let's turn the page over and let's take a look at the horizontal cylinder. Oh, and by the way, before we leave here, there's a question that sometimes comes up. What about a vertical cylinder? How do we deal with that?
Horizontal flat plate.
Pardon me?
Horizontal flat plate.
Vertical cylinder.
Yeah. So would you treat the bottom as like a flat plate?
No, it'd be like a pipe running like this. This would be a vertical cylinder. I'm not sure what you talk about in terms of the bottom. This little area here.
Can you unwrap it?
Thank you. You unwrap it. So in other words, you unwrap it. Think of a cigar. You kind of unwrap, all right? Now, there are criteria for that. Go back here to page 570. No, that's not it. Oh, and let me unwrap it, and it's in here, and I'm having can't seem to find it, but that's what you do. And the criteria in here, I'm not going to have you unwrap it in a test, but just know that that's what you can do. But there is, while we're here, worth talking about one thing. The characteristics, 924 is an equation for an isothermal plate. Okay, that means it's constant temperature. What happens when you have a constant surface heat flux? all right? What you do is you can use the same correlation, but notice at the very bottom of the page in 573, what you want to do is you want to, not at the very bottom, an approximate halfway through that bottom paragraph, I should say, and I'll read the bottom paragraph for you. It is important to recognize that the foregoing results have been attained for an isothermal plate. If the surface condition is instead one of uniform surface heat flux, the temperature difference will vary with X, increasing from the leading edge. An approximate procedure for determining this variation may be based on results showing that the average Nusselt correlations obtained for the isothermal plate may still be used to an excellent approximation if the Nusselt number and Rayleigh number are defined in terms of a temperature difference at the mid-plate point of the plate. That is T being evaluated at the middle of the plate, and then your properties being based on that film temperature. Okay? All right. So that. All right. Let's go now to back to 9.2 and look at equation 933. All right. Again, I direct your attention now to page 581 in your textbook. And I got to tell you something. It really is very useful to use a little highlighter at this point, so when you're looking at this in the midst of a test, you remember that you have to. What was the coefficient? What is the exponent? But if you don't remember, it's easy.